No, we're gonna do stuff. Okay. First thing, I gotta show you the spinny. Okay, I'm into that. Look. Okay.
It's great.
Think about what we learned about yesterday. Watch this. I'm gonna impart a torque. I'm an external force right now. So, okay, so I just changed its angular momentum. But now, look at that.
Whoa.
And go back out. Fast. Slow. Fast. Slow. That's how you think. And here, I gotta show it to the Twitch followers. Hey, Twitch super fans, make sure you send the 100 bits. Send the bits. Send bits. Send bits. No.
Some of the uncapped.
Anyway, supposed to you spin, and then you go whoop, and then it goes fast, and it goes slow. My arms are too short. Okay. Anyway, so where's the markers? So it's interesting with that. Think about it. So then the point is, so why does it do that? How come it speeds up when you compress it? Well, it's very much not obvious, but like, are you really exerting a torque when you shrink it? Because I am pulling on that string, but this is the axis of rotation. And so the way that torque works, so when I first pushed it, I had to exert a force, like say out here, right? Torque is force times radial distance. But if the force is happening on this axis in this direction when you pull the string, there's not really a tangential component there. So really, you don't want to think about it in terms of like a torque. What you want to think about it is this. What happens when he goes shrinky winky? What happens to this? It decreases. Okay. So when it shrinks, I decreases, and because angular momentum is conserved, that means that this has to increase by the same proportion. Cool beans? Yay! Okay, we got it. So let's look at a couple problems together. If that's okay with you, Kate. Good. Okay. Let's do the I don't know. Let's do a simple one and then like a little bit more complicated one. Let's look at 11. So astronaut Bob is spinning. Doesn't say what direction he's spinning, but it doesn't really matter for the question. Let's just say he is spinning along a vertical axis. He's just spinning like this. Okay. So this says when he tucks his arms in, he increases his rotational rate. Does that make sense? Why? We're all okay with that, right? If he tucks his arms, he's going to speed up. So the question is, what's the relationship between his I values if his angular velocity increased by 40%? So let's call this maybe omega naught. If his angular velocity increased by 40%, what's his new angular velocity? Anyone?
Yeah.
So I'm saying it says his angular velocity increases by 40%. So if he initially had an angular velocity of this, What's the new one?
1.4.
Right?
Mhm.
We understand? That's 40% bigger than that, right? Okay. So let's see. L equals, so his initial angular momentum is his initial I value times his initial omega value, right? So here's the thing. What happens then? What happens if you are multiplying this number by 1.4? What has to happen to this number?
Decreases.
By 1.5.4.
It's being divided by 1.4, right? So if you want to do algebra, what you might say is, well, in this case, his L value is the same. His I value is what we want to know about, we're solving for. And his omega is 1.4 omega naught. So when you solve here, tell me if this makes sense what I'm talking about. And how does that compare to what I had before? Oh, well, my new I value looks a lot like my old I value, but it's divided by 1.4. Okay? So the answer to the question is the new I value is the old I value divided by 1.4. But let's put it into perspective of like percents. So say I want to phrase it like this. When he, in order to increase his angular velocity by 40%, he had to decrease his I value by, nope.
60%.
Well, who's our friend here? Mr. Quackmolator. Okay, can you tell me what 1 divided by 1.4 is?
Point 7142.
0.714. Let's just leave it like that, I guess. You guys see what I'm talking about? So how much did his I value decrease? How much percent? No?
29%.
29.6%. No, 28.6%? You guys see what I'm talking about?
Yeah.
Okay, so that's maybe a little counterintuitive result, right? You might have thought, oh, increase by 40 corresponds to a decrease by 40. Well, that's not quite how it works when you're talking about percents, right? For example, okay, so let's go back to simple stuff. If I doubled this, say I wanted to double this, what happens to this? You cut it in half, right? But think about percents. If you double something, that's 100% increase. And when you cut something in half, it's a 50% decrease, right? Say you're talking about tripling. If you triple this gets divided by 3, right? Well, tripling something is a 200% increase, and dividing by 3 is a 66.6 repeating percent decrease. That make sense?
Yeah.
Yeah? Right? I'm just saying, like, percents are. Same thing with, like, distance and velocity. It's like, you guys remember doing these back in kinematics? Like, distance is velocity times time if you're assuming you're having a positive velocity. And you say, well, let's say I increase the velocity by 25%. How does that affect my time to travel the same distance? Right? So I usually go from here to there. It takes this much time. Let's say I go 25% faster. Well, let's see, if you multiply this number by 1.25, you have to divide this number by 1.25, right? And if you divide by 1.25, that's 5/4, so that would actually be 0.8. So if you increase your velocity by 25%, you're actually decreasing your time by 20%. Okay. So anyway, so this one we were decreasing. So there's two ways to, I guess, write the answer. All right. Feel okay? Yes.
Can you do it with improper fractions and reciprocals? Does that work?
Yeah. Like this is 7/5.
Mm-hmm.
So yeah, so L divided by 7/5. So you could say, oh, I had 5/7 of L naught.
Mhm.
Yeah, definitely. Good point. Okay. So, I want to talk about the car, Mr. Zoom Zoom race car. So take a second and read the question. All right. Does anyone have an idea for an answer?
I almost say you want his break.
I'm thinking the
Brakes?
brakes, dude, because like the idea is if he's spinning the wheels, it's like they can go more forward.
That's what I see. Yeah.
What?
They're time racing.
Yeah.
Like when you're in the air.
Is that like a sport?
Yeah. They'll climb
That's
up
a video game.
like razors and snowmobiles.
So what would, if you were playing a video game, what would you do?
Yeah. You just never let off the gas in a video game, Mr. Hall.
No,
you let
no.
off or you'll die. That's just
Okay.
a state of mind.
So,
Yeah, it's a state of mind.
so here's the car.
I haven't played a racing game, so.
Good enough. Okay, there's the car. So there's the front windshield. So he's going from right to left, and he realizes that, so by the way, the car is, what direction overall is the angular, well, what direction is it rotating? Counterclockwise. What direction are the wheels spinning?
Right.
Same way, right? I mean,
Yeah.
right? He's driving this way, so the wheels would be spinning in the. It's not like anything crazy. He didn't switch into reverse halfway in the air, and no, nothing crazy. Okay, so overall, this system has a bunch of angular momentum, right? Now, here's the thing, though. Let's say he. Now this is going to be conserved, right? The total angular momentum in this system. Okay, so what would happen if he made these arrows bigger? What would happen if these guys both went bigger? What would have to happen to this one? It would have to get smaller. Conversely, what if he made these arrows smaller? This would have to get bigger because, again, the total, L total, is conserved. So I might say the L total is something like the L from the frame plus the L from the wheels. So if the wheels increase their angular momentum within the system, then the frame would have to decrease in response. That make sense? So therefore, and what's his goal? He thinks the frame is rotating too much, right? So he actually wants to decrease this angular momentum, right? So what's the answer? He should hit the gas.
Yes.
He wants to increase these. Okay? Is he changing the angular momentum of the system? No. Because there's an engine in there, but that's inside the system. It's a closed system. So he's not changing the angular momentum of the system, but he is changing the angular momentum of the wheels, which then changes the angular momentum of the frame. Okay? It's actually a very complicated system because the wheels are spinning, but the wheels are also rotating around the center of mass of the system. But
I feel like you would have crashed if you would have just found that information out now.
well, I think they know this before they do the jump. Is this how? Wait, what's that game called? Hill race? Hill climb racing? Is this how? If your car was? I mean, does it work like this? Does your car like over rotate and you have to hit the gas to slow it down? Is that how it would work? Lit. That means that game is lit. Okay. 16 is kind of a funky one to think about. If the total angular momentum of the system comprising Earth and everything on it is conserved, which it should be. Here's Earth. Earth. Okay. There's Earth rotating. Here's Mr. Teletubby. Okay. And of course, there's a bunch of stuff on Earth, weasels and stuff like that. What happens if you're one of those particles that lives on Earth? Say you're in your car. What happens when you drive east?
Technically, you're slowing down the Earth.
There you go.
No, you're going.
Well, you're maybe from a perspective of an observer outside the Earth, they might say, "Oh, you're going faster." You can calculate the speed of a single point on like the equator. It's pretty dang fast if you calculate it. We can calculate it real quick. That'd be fun. Well, it's an easy calculation. What's the radius of Earth? That one we have to look up, but I think it's 6,400 like kilometers. Let's Google it. Radius. Wait. So the radius is 6,400 kilometers. So that means the circumference of Earth is 2 times pi times 6,400 kilometers, right? And so that means the speed of a point on Earth would be that distance divided by, let's put it into kilometers per hour. So that makes sense, right? How many hours does it take to rotate around? 24. So then Mr. Clackmulator,
I got it. 1675.52.
0.5
Yeah.
kilometers per hour. So, and there's roughly 1.6 kilometers in every mile. So you could, I guess, divide this by 1.6 to get roughly 1,000 miles per hour if you want. I think that's right? We didn't make any mistakes there, right? So a point on the equator travels about 1,000 miles per hour. So anyway, if you were driving 100 miles per hour from a stationary observer, they'd go, "Whoa, you're driving 1,100 miles per hour." Whereas if you were driving west, they would say, "Oh, you're driving 900 miles per hour." Is this making any sense? Are you bored to death? Okay. Anyway, so so you're part of the total angular momentum system here. So let's say you're considering this to be your closed system. You're part of that closed system. So if you start driving, so then if I said, okay, the total angular momentum is the angular momentum from the planet plus the angular momentum of you, right? Or maybe this would be the angular momentum of the planet and everything else. And this is plus you and your car, your contribution. It's a very small contribution, but it's there. So if you are going east, are you like, is this number increasing or decreasing? If you're going the same, just in case anyone doesn't know, the Earth rotates. The sun rises in the east and sets in the west. Just throw that out there. So the Earth is rotating this way. The Earth is rotating. That's why the sun rises in the east, by the way. It's because this Earth is rotating this way. So.
How else the big solar lamps?
Oh, true. Yeah, exactly. So anyway, so what do you think? If you go this way, is that going to decrease this or increase it? It's going to decrease it because you're adding. So I'm saying if you speed up in this direction, you're increasing this number. So this number has to decrease ever so tiny to keep this the same. Conversely, what if you go this way? You're actually making this a negative number now because you're going against, which means this number will have to get a little bit bigger in order to keep that the same. Okay? So there you go. You can feel. I believe it was a Superman movie where he, it's not this exact principle, but he like runs around the earth to like. Well, yeah, he changes the direction, which also somehow makes time travel backward. That it would, in principle, be possible, I think, to reverse the rotation of Earth if you could somehow had like a Superman type, some kind of external torque on the Earth that you could get it to rotate the other way. I think it would not reverse the flow of time. I don't think. Probably not. Haven't tried it. Yeah. Okay. Guys, we're gonna move on to like, I think up tomorrow I'll do a couple examples like 25, 26-ish. But make sure you're not falling behind. We're almost done. We're gonna have a quiz on this really soon. So maybe Monday. Monday maybe? Okay.